Hello again, Foundation students, and welcome back. So today we're going to talk about functions. And functions are one of those topics where you have some familiarity with the topic because in several previous courses you've dealt with functions. But probably for the most part your experience with functions has to do with real valued functions. So functions like f of x equals x squared, and you did calculus with these type of functions. But now we want to expand the notion of what we mean by a function and make it a more general construct that can apply to more than just real numbers. We want functions to be able to apply to sets, to be able to apply to complex numbers, to all kinds of stuff. So having functions built on the idea of sets is going to be pretty powerful. In fact, functions are going to be built on the previous notion that we've talked about, the previous notion being relations. So a function is going to be a special kind of relation. So let's get into the definition here. So a function is going to be a relation from a set A to a set B, and we're going to require that the domain of our thing we call a function is going to be all of the first set A, and we'll use this notation here to indicate a function from A to B. And the key property, though, of being a function is this property here, that if you have two ordered pairs in the function that have the same first component, then the second components must be equal. So in this notation here, f colon A arrow B, the first set here is the domain of the relation, and the second set is called the codomain. The set B is not exactly the range of the function, but it contains the range. This ordered pair-based definition of functions is kind of handy because functions are relations and relations are collections of ordered pairs. So whenever we want to think about functions on the order of them being relations and using sort of set theoretical proofs of things involving functions, sometimes converting things into ordered pairs like this is kind of nice. How I think of a function more intuitively is that a function is a relation from A to B with the property that every element of the set A is the first component of exactly one ordered pair in F. So it's just saying that you don't see the first component of an ordered pair appear more than once. So each first component appears only once in the function. So if we take that definition in the blue box there and sort of break it down, it really just means three things. The first thing that this f colon A arrow B notation tells us is, one, it tells us that the domain of F is exactly equal to A. The second thing it tells us is that the range of F is a subset of B, but not necessarily equal to the set B. And then the third property, which I'm going to call the function property, is this property that if you have two ordered pairs with the same first component in F, so A comma B and A comma C, if those are in F, that implies that B must be equal to C. So in other words, there wasn't really two ordered pairs with the same first component. If that same first component appeared twice, it must be the case that the second components were actually the same, so that you were really only talking about one ordered pair there. Okay, so let's look at a few concrete examples. We'll start with sort of a toy example here involving just some finite sets and some ordered pairs. So let's look at the first function, or the first relation here, f, which consists here of three ordered pairs, 1 comma delta, 2 comma beta, 3 comma beta. Notice that all of these three relations are relations from A to B because all of the first components that you see in the ordered pairs are coming out of the set A, and all of the second components are Greek characters coming out of the set B. So all of these are relations from A to B. But I want to know, is it the case that these are functions from A to B? So we can think about those three things above. Does the relation have the right domain? Is its range in the right place? And does it have the function property? So the first example there, you can see, yes, it is a function. F here is a function from A to B, which we can say that that whole sentence we can indicate with this shorthand, f colon A arrow B. Because what's the domain of F? Well, the domain of F is the collection of all of the first components that appear in that relation. And you can see 1, 2, and 3 are all present. So the domain is equal to A. The range is contained in B because the range is the set of all second components of the ordered pairs, and those second components are all inside of B. Now we didn't get everything back in B, so we know the range is a subset of B, but it's not necessarily equal to B. And lastly, we definitely have the function property because if we think about what that means at the very top there, it just means that every element of A appears exactly once in an ordered pair. So 1 appears once as a first component, 2 appears once as a first component, and 3 appears once as a first component. If I would see, say, 2 appear twice, I'd know I'd have a violation of the function property. Okay, let's look at G there, the relation G. Is that a function from A to B? Well, check it out. When you look at this ordered pair 1 comma alpha, and you look at this ordered pair here 1 comma gamma, we have the same first component appearing twice, but those second components aren't the same. So G is not a function from A to B because we have this thing going on where 1 comma alpha and 1 comma gamma are in G, but alpha does not equal gamma. Now, G does have an okay domain. The domain is all of A, and its range is contained in B, but it just doesn't have the third function property. And lastly, H is also not a function. It doesn't violate the property of the range being in B, and it also doesn't violate the function property, the third thing at the top, but the domain's not right. The domain of H is equal to 1 comma 2, which does not equal A. So I can't say that this is a function from A to B. I could say H is a function from the set containing just 1 and 2 to the set B, but I can't say it's a function from A to B. When something like that happens, a common thing that we do is we restrict the domain to an appropriate set where we do get a function. So in the case of H, if I just restricted the domain to 1 comma 2, then I could say I've got a function from that set, 1 comma 2, to the set B. Okay, now it's always true when you're talking about a function, you're talking about a collection of ordered pairs. And so ordered pairs, I mean, when you think of a function, you can always think of its elements as ordered pairs. But of course, in your past courses, you never thought about functions as ordered pairs, really. You use different notation to indicate the function relationship between two elements. So what you would do in the past is write something like this. You'd write f of A equals B. So this will be our notation that we commonly use when we want to say A is paired with B in a relation that's a function. Now, if f was just a relation that's not a function, I wouldn't use that notation. So when I use that notation, it indicates that we're talking about a function. F is a function. Okay, so that notation is reserved only for functions. And when we use that common function notation, we can recast the definition of function in terms of that notation. And so in this box here, this highlighted box, I do exactly that. We can say f is a relation from A to B, with the domain of f equal to all of A, so that's sort of the part one. And because it's a relation from A to B, it's automatic that its range is a subset of B. And then the function property part of being a function is in orange here. You can characterize that as for every A1 and A2 and A, if A1 is equal to A2, that implies that f of A1 equals f of A2. And sometimes this is a little bit easier to work with than the ordered pair notion. But both are valid, and you can work with both in proving something is a function. We'll come back to proving things are functions shortly, but first I want to talk about visualizing functions and non-functions. So whenever we're dealing with the sort of bubble diagram picture of a relation, we can tell at a glance whether or not it's a function. So this first one over here, f is a function, because I can look at it just at a glance. I can see that the domain is all of A, because every element in A has an arrow coming out of it. I can tell that the range is in B. The range is the set of elements in B that have an arrow pointing toward it. So the range here is 1, 2, and 3. And then it has the function property because when I think about those arrows as indicating ordered pairs, I don't see two arrows emanating from a single point. So every element in the domain only appears once as the first component of an ordered pair. Or visually, each element of the domain only has one arrow emanating from it. Whereas in the second picture, the relation G here is not a function from A to B. Because I can see that A, 2 and A, 3 are in G, but those second components are not equal. But at a glance, I can just see that I have two arrows emanating from a single point, so it's not a function. The domain and range part are okay. In this case, the domain is equal to A, and the range is actually equal to all of B, but that's a subset of B. So the domain and range part are okay, but it fails the function property. And whenever we look at relations defined by equations, like we have here in these two examples, so the relation on the left is defined by the equation y equals x squared minus 4, and that's our old friend, a parabola. And then the one on the right over here is defined by the equation x squared divided by 9 plus y squared divided by 4 equals 1. You may recognize that as the equation of an ellipse, which has the minor axis of length 2 and the major axis of length 3 there. Now I can also tell at a glance that f is a function, but g is not a function. And you may remember something called a vertical line test. The vertical line test says if you can draw a vertical line through the graph and it crosses twice, then the relation is not a function. Now on the parabola there, any vertical line that you draw only crosses that graph once. But on the parabola over here, when you draw vertical lines, it can happen that the vertical line will cross the graph twice. In particular, if you would look at just the y-axis there, the y-axis crosses at 2 points. So check it out on G here. You can see that 0, 2 and 0, -2 are in that relation G. In other words, those two ordered pairs satisfy the equation that defines G, but those second components are not equal. And that's being captured by that vertical line test, right? Because those are the points where the vertical line in red here crosses the ellipse at those 2 points. So that's why the vertical line test is kind of a nice visual. It gives you a quick way to find these 2 points that violate the function property. So you get the 2 points, but their y components are not equal because they're crossing the graph at 2 different heights. Now the vertical line test is just a visual heuristic. It's not itself a proof of anything, but you can use the information that you glean from a vertical line test to get a proof. So like what I've written here about the ordered pairs is part of a proof that G is not a function from say R to R or whatever set you want to use. Next little topic that I want to mention is that there are equivalent ways to describe a function. The first and most foolproof being to use set builder notation. Functions are relations and relations are sets. So if you describe your function as a collection of ordered pairs, then you can't go wrong. It's maybe the most bulky way to define a function, but it's the most foolproof as well. So in this first notation here, f is a set of ordered pairs in R squared, and I've got a defining equation there, y equals x squared minus 4. That's the one we did at the top there, that parabola on the left. And another way to do it is to use the function notation to basically state what the domain and codomain are, and then you give the equation that defines the function. Putting this set here is basically telling you where the first components are coming from. The second copy of R here is telling you where the second components are coming from. And then this equation here is just doing the same thing that the equation did here in the set builder notation. That works also, and that's probably the most common way to define a function. And then lastly, if the domain is understood from context, sometimes we'll just state the defining equation. So if I was in calculus class and I said f of x equals x squared minus 4, you would understand that I'm only talking about putting real numbers in there. So you would understand just from context that the domain is really just the real numbers. You wouldn't be thinking about putting complex numbers in there in calculus class. So if the context is clear, you can get by without being so precise about stating domain and range, or domain and codomain. But when in doubt, I think either one or two are the way to go. So next, let's talk about how do we prove that a given relation is a function. Let's do it for this example here. So G is, I'm using the set builder notation to define G. It's a set of ordered pairs in R cross R with the stipulations that the first component can never equal 2, and the second component is equal to 1 over the first component minus 2. So I want to prove this fact, that G is a function from the set R minus the singleton 2 to R. So that notation there entails three things. It entails that G is a relation with the domain of R minus the singleton 2. Secondly, that the range of G is contained in the real numbers. And then third, G has to have the function property, which is basically that the first components in the relation only appear once in the relation. Let's do it. We're going to break it down into those three parts. So we're going to prove 1, domain of G is exactly equal to R minus the singleton 2. 2, that the range of G is contained in R. And 3, we're going to prove the function property that for every, let's say, x1 and x2 in the domain of G, if x1 equals x2, then f of x1 equals f of x2. So equal inputs give equal outputs. In proving 1, let's think about what we got to prove here. We got to prove domain of G equals R minus the singleton 2. What kind of objects are we trying to prove are equal here? That's right, these are sets. And so we know how to prove set equality. Our standard way of doing that is to do a double containment proof. So let's do that here. All right, so let's prove the forward containment. So we got to start by letting some arbitrary element, let's call it x, be in the domain of G. So first, since G, when we look at the definition of G, the ordered pairs are in R cross R. And so that tells us that G is a relation from R to R. So since G is a relation from R to R, then domain of G is a subset of the real numbers by definition of domain. The domain is always a subset of the first set in the relation. You know, the relation's going from A to B, then the domain's a subset of A, just by definition. So we know X is a real number because X was in the domain, which is in the reals. Now, since X is in the domain, we can apply the definition of domain. And remember, the definition of domain is it's the set of all first components of ordered pairs that exist in the relation. So X here has to be the first component of an ordered pair that's in the relation. And if it's the first component of an ordered pair, there has to be a second component that goes with it. So there exists some Y in the second set in the relation. This relation goes from R to R. So the second set is R. So there exists some Y in R such that the ordered pair X comma Y is in G. And then next we can think about, what does it mean that X comma Y is in G? Well, we have membership conditions up here. That means that the first component is not equal to 2 and the second component is 1 over the first component minus 2. So since X comma Y is in G, we know X does not equal 2. And we happen to know also that Y is equal to 1 over X minus 2, although that bit's not super important right now. In particular, X does not equal 2. And so when we pay attention to the information that we have written down in the proof so far, we know that from earlier we knew X was a real number, and now we know X is not equal to 2, but that's exactly what it means for X to be in the set R minus the singleton 2. So now we have X is in the reals, and X is not equal to 2, so X is an element of the real numbers remove the singleton 2. And now we have proven the containment that we wanted to prove, because we started with x in the domain here, and then we arrived at x was in R minus 2. So there we have it. Let's do the reverse containment next. So here we're going to let x be in R minus 2. And we want to argue that x must be in the domain. Well, all we have to do is point out that x is paired up with some second component in the relation, so that we get an ordered pair in the relation where x is the first component. Well, we know what x has to pair with. If it's going to be a first component in the relation, it's got to pair with 1 over x minus 2. So we just need to point out that x is not equal to 2. So 1 over x minus 2 is a real number. If you take, as long as you do 1 over a real number that's not equal to 0 in the denominator there, then you get a real number. So thus, by definition of G, the ordered pair x comma 1 over x minus 2 is in G, because the ordered pair satisfies the membership conditions of G. The first component's not equal to 2, and the second component needs to be 1 over the first component minus 2. So thus, x is an element of the domain of G, because I'm looking at the fact that x is the first component of an ordered pair in G, and that's what it means to be in the domain. So we started with x was in R minus 2, and we arrived at x is in the domain. So now we've proven that the domain of G is equal to all of R minus 2. So now we'll move to the next part, and we'll prove 2, that the range of G is contained in R. So here we need to just prove a regular old containment. So we'll element chase it. So we'll start off by letting, let's say, y be an element of the range of G. Well, if something's in the range, that means it's got paired up with some first component that's in the domain. So then there exists some x in the domain of G, which we just proved, by the way, is the set of real numbers minus 2, such that the ordered pair x comma y is in G. Now x is not equal to 2, and we know that the y there has to be equal to 1 over x minus 2 on account of the ordered pair x comma y being in G. That's the membership conditions that have to be satisfied. Well, since x is not equal to 2, then the number y equals 1 over x minus 2 is a real number, because you're not dividing by 0. So if you do 1 over a real number that's not equal to 0, you get back a real number. This is sort of like some assumption about the real numbers that we're making here, but it's certainly true. All right, and then there you have proven the containment, because we started with y was in the range of G, and then we argued that y was in R. That was the containment we wanted to prove. Okay, then the third thing we need to do here is to prove the function property. So we're going to start off by saying, let's let x1 and x2 be in the domain with x1 equal to x2. Then we know that g of x1, according to the definition of the function, that would be 1 over x1 minus 2. But because x1 and x2 are equal, then this is equal to 1 over x2 minus 2, which in turn is equal to g of x2. And now we've proven all three properties of what it means to say f is, or g is a function from r minus the singleton 2 to r, and so we're done. When you're dealing with just real valued functions, it's often kind of obvious that when you're dealing with a function or a non-function, what you really have to worry about is, a single x value is going to somehow result in two different y values. And when you're talking about real numbered sort of equations, it has to be some sort of situation where when you solve for y in terms of x, you get like a plus and a minus, or some sort of thing like that. So it's kind of obvious when you're dealing with real numbers, but there are other situations where it's a little more subtle. And so this proof here is meant to just be sort of a template for you. How you prove things in general are functions, but it's not that insightful in terms of giving you examples of functions that are not functions, or examples of relations that are not functions. So let's take a look at a couple of things that are not functions. In this first example, I've got this relation here. It's a set of ordered pairs in R squared. So this is a relation from R to R. And then the defining equation is the x component is the square of the y component. Now, if you would graph this, do a quick and dirty graph here, it looks like this. So it's a sideways opening parabola, and we can see visually that it does not pass the vertical line test, right? So to prove something is not a function, you just need to give a couple of points on one of those vertical lines and say, look, here's a couple of points with the same x component but different y components. So in particular, you could take when x is equal to 1, then you get two different y values. You get y equals +1 and y equals -1. Using the graph as our guide here, our proof that p is not a function would go something like this. P is not a function from whatever set. I mean, I guess we could, the natural domain for this relation is 0 to infinity, just looking at the graph, to the real numbers. Since we see that 1, 1 and 1, -1 are both elements of this relation P, but the y components there are not equal. So that's it. That's a proof that P is not a function from the interval 0 to infinity to the reals, because it fails the function property. Now here's a weird example, and this one really gets at why checking the function property can sometimes be a subtle thing that needs to be checked. I mean, this looks like a perfectly reasonable equation. I'm making a function, and it takes as input fractions. So, you know, the rational numbers are just those fractions where the numerator and the denominator are both integers. So a and b here are both integers, and b is not equal to 0, so we can't divide by 0. And I'm just going to take the numerator squared plus the denominator squared. Well, that seems like a perfectly fine thing to do. What's wrong with that? I can certainly do this formula for the domain of this relation here. P is actually equal to all of the rational numbers. I can do this formula for any rational number. A and b are just integers, right? And so I can do a squared plus b squared for any two integers, no problem. And two, you can see that the range is contained in the natural numbers, because a squared and b squared are non-negative, but b is not equal to 0, so I'm going to always get a positive integer for an answer here. I definitely get output values in the natural numbers, so the range is contained in the natural numbers. But that function property is where this one breaks down. So check it out. This is kind of cool, I think. The function property is not satisfied, and here's why. Check it out. Let's let x1 be 1/2, and let's let x2 be 2/4. Observe that x1 equals x2, but so basically we've got two different representations of the same number, but the way the function works, it depends on the representation of the number. So p of x1, so that's p of 1/2, that would be 1 squared plus 2 squared, which is equal to 5. But p of x2, so that's p of 2/4, would be 2 squared plus 4 squared. So that's 4 plus 16 equals 20. P of x1 certainly does not equal p of x2. So what the point is here is that this formula has ambiguity, right? Like if I put in the same number, depending on the form of the number, I get different outputs. And that's exactly what we're trying to rule out when we're talking about functions. Functions are relations that relate to elements in an unambiguous way, okay? So this formula, which looked fine, you know, on the surface, is extremely ambiguous. And functions are exactly the kind of things where we're trying to eliminate ambiguity. So this is not a good function. It's a relation though, okay? P is a relation. It's a relation that every rational number gets actually paired up with infinitely many different y components. And that's okay in a relation. We can have relations that do that, but in a function, we got to disallow that sort of ambiguity. Okay, let's do a quick skills check on functions and non-functions. So I have 3 problems I want you to try out here. The first one's similar to the toy example I worked, where we have some functions defined as finite sets of ordered pairs, and we just want to examine which of those are functions from A to B and explain why or why not. Next, we have a relation, G, defined using set builder notation, and we want to we want to talk about using this notation, G colon A arrow to R, and then we want to know what is the biggest set A in the reals that would make this statement true, that G is a function from A to R. And the biggest subset A of the reals that you can find that makes G a function from A to R is called the natural domain of G. So basically I want you to find the natural domain of that function. And then lastly, I want you to use the method we did previously for how do you prove something is a function. And the function here is defined by 3 divided by the quantity 1 plus x squared. And I want you to prove that it is a function from R to R. Okay, so pause your video and take a swing at these problems, and after you've had a try, then we'll work through it together. All right, welcome back. So let's take a look at number 1. For each of these 3 relations, we want to know, is it a function from A to B? So this notation like f colon A arrow B means 3 things, right? It means 1, that the domain is A, 2, the range of f is contained in B, and 3, it has the function property, which means that you never see the same first component of an ordered pair appear twice in the relation. So we can just examine these and answer all of these questions pretty quickly. So let's look at part A, the function f. So let's check the domain part. Is the domain all of A? Well, I see 1, 2, 3, 4, 5, and then I see 3 repeated. But for the domain is 1, 2, 3, 4, and 5, which is all of A. So that checks out. How about the range? The range has to be inside of B. So that means that all of those second components have to be elements of B. So I've got alpha, beta, epsilon, delta, alpha, epsilon. Those are all elements of the set B up here, right? So that means the range is contained in B. And lastly, I have to check, does f have the function property? So the function property means you never see the same first component repeated, or if it is repeated, it's paired with the same element both times. So do I have any repeated first elements? Well, I see 1, 2, 3, 4, 5, and then 3 again. So 3 is repeated here and here. But notice that the element that 3 is paired with is epsilon both times. So what's really going on is that I've just repeated this ordered pair twice. So it's redundant, right? I can just basically get rid of that 3 epsilon because I've already got 3 epsilon over here. And because of that, it's still a function. So I do have a repeated first element, but it's paired with the same second element. So f is a function, having checked all 3 properties. Let's check G. Same sort of considerations. The domain of G, I got 1, 3, 4, 5. Uh-oh, I see that I'm missing the element 2 from the domain of G. So the domain of G is not all of A. So it's not a function from A to B. It's a function from some subset of A to B, but it's not a function from A to B. So G is not a function from A to B, since the domain of G equals 1, 3, 4, 5, which is not equal to A. G does have the function property though, because you don't see any repeated first components in the ordered pairs. Okay, now let's look at H. So first we'll check the domain. We get 1, 2, 3, 4, 5, and then 3 again. But the domain is all of A, so that checks out. Let's check the range. Is the range contained in B? So we just want to check that all of those second components are elements of B. So I got alpha, beta, epsilon, gamma, alpha, gamma. All of those are elements of B, so the range checks out. And then we need to check the function property. So we look through here and we want to see if there are any repeated first components, and if there are, we want to make sure that they're not. We want to see whether or not the second components are the same or different. So I see that 3 epsilon and 3 gamma are in this relation, but here the second components are different. So 3 got paired up with 2 different elements in the range, so that means this H does not have the function property. So H is not a function from A to B. It fails the function property. Okay, all right, so let's take a look at number 2. So the idea here is we want to figure out what's the largest possible domain for this function that would be a subset of the reals. And of course we call that the natural domain. So when you look at this relation, the equation and the membership conditions here that define that relation, it's expressed x in terms of y. And usually we want to express the second component as a function of the first component, but it's got it the other way around. But that might be a little bit of a worry, but we should check that this equation, x equals the square root of y minus 1, if you square both sides of that, you get x squared equals y minus 1. So that's really the same as y equals x squared plus 1. And you may recognize that as a parabola that's shifted upward 1 unit. So it's a function. I don't get 2 different y values for each x value. But when you think back to the original relationship, what possible values can x be? The x values are the domain values. Well, we can see that y has to be bigger than or equal to positive 1, right? And if y is larger than or equal to positive 1, that implies that x equals the square root of y minus 1 would have to be greater than or equal to 0. So this is what we're looking for here. The x's we can see correspond to positive values. So our natural domain here would be the interval from 0 to infinity. So if we write g 0 to infinity to the reals, 0 to infinity would be the domain of that function because the x values have to be non-negative by this equation here. And so if you think about the graph of this, you're not getting the full parabola defined by this equation. You're only getting the ones for the x values where it's positive. So you'll get like the right-hand half of that parabola like that. Okay, let's take a look at number 3. Here we have a function defined by the equation 3 over 1 plus x squared. And we want to prove it's a function from R to R. So here's what we have to do. We have to establish 3 things. 1, we need the domain of f to be all of R because we're trying to establish that this is a function from R to R. So the domain has to be all of R. 2, we need that the range of f is a subset of R because R is our B set here. And you need the range in general to be a subset of your B set. And 3, we need that function property to be satisfied. So let's go through and do these 3 properties. So 1, we need to show that the domain of f is equal to R. Okay, so to establish that the domain of f is equal to R, we might use a double containment argument. Now, the containment that the domain of f is contained in R is basically a given because from the context of the problem, it's clear that we're defining this function f of x equals 3 over 1 plus x squared for real numbers. By context, it is clear that f of x equals 3 over 1 plus x squared is defined for real numbers. So, in other words, x is a real number here. And consequently, the domain of f, that's all the x values, is a subset of the reals. The other direction is typically the more interesting direction. I want to take an arbitrary real number, let's say x is in the reals, and I want to show that x is in the domain. So that means I need to show that x can be paired up with another real number y according to that formula. Well, this is not a problem. Then note that 3 over 1 plus x squared is a real number too. Because if x is real, then if you do 1 plus x squared, that's real, and then 3 over that's still a real number. The only way you don't get a real number is if you maybe divide by 0 or take the square root of a negative number. So 3 over 1 plus x squared is a real number. So if we let y equal that 3 over 1 plus x squared, then f of x equals y, or in other words, x comma y is an element of f. So x is paired up with something in the codomain as an ordered pair in that function. That means x is in the domain. Okay, so indeed the domain is all of R. Any real number. So basically we're just saying any real number can be plugged into that formula, but doing it more formally with sets. Second thing we want to establish is that the range of f is a subset of R. So to do that, let's let y be an element of the range of f. Well, that means there exists some x in the domain, which we already established was the real numbers, that pairs up with y. And if we use the function notation, that means that f of x is equal to y. That is, remember, f of x is 3 over 1 plus x squared, and we see that since x is a real number, y equals 3 over 1 plus x squared is a real number also. This is the same observation we made earlier. So if you look at what we've done at this point, we started with an arbitrary element in the range, and we argued that that very same element's in the reals. So that proves that containment. The third thing we have to do is establish the function property. To do that, we take two arbitrary elements of the domain of the function, and we assume that they're equal. And then we want to show that the corresponding function values are equal. It's usually a pretty straightforward thing to do here. So f of x1, according to the definition of function, that's 3 over 1 plus x sub 1 squared. But because x1 equals x2, that's equal to 3 over 1 plus x2 squared, which is equal to f of x2. So the broad strokes here are we started with x1 equal to x2, and then we argued that f of x1 equals f of x2. And so that establishes the function property, and we're done proving that f is a function from R to R. So every time you see that notation and someone says prove it, you got to prove three things. The domain is the A set, the range is contained in the B set, and it has the function property. All right, next up, we want to talk about the concept of a function being one-to-one. So if you have a function, f colon A arrow B, so again, that means f has domain A, range contained in B, and it's a function. So it's one-to-one, or sometimes we use the word injective, and we denote it by 1-1 there. If for every two elements in the domain, anytime f of a1 equals f of a2, then it must be the case that the a1 equals a2. So I think of this as if the outputs are equal, then the inputs must have been equal as well. So let's consider a couple of examples here. Here we have a couple of standard functions. On the left here we have the function, the linear function, f of x equals 1/2 x minus 1. And on the right over here we have the function g of x equals x squared minus 4, so a parabola pointing upward. And you can actually tell just by looking at the graph that whether the function's one-to-one or not. See, one-to-one means that you don't get the same y value from two different x values. So on the graph at right, you see that, let's say if you draw, a horizontal line right here, say same height as the x-axis, you can see that in fact there are two x values corresponding to the same y value. Here at x equals 2 and -2, those two x values yield the same y value, y equals 0. Or down here at x equals -1 and x equals +1, we're getting the same y value of -2. So you see you've got 1, -2 and -1, -2 are both points on the graph, so you're getting the same function value, that's the y value, but two different x values. So that violates the definition of one-to-one. On the other hand, the graph on the left, whenever you draw any horizontal lines, it only crosses the graph once, no matter where you draw it. So this brings up the horizontal line test. The horizontal line test just says that if you can draw a line that intersects the graph twice, then the function's not one-to-one. Or to put it more positively, if every horizontal line crosses the graph at most once, then the function is one-to-one. So here on this graph, it fails to be one-to-one, the graph of g, because you have f of -1 equals -2, and that's the same as f of +1, but -1 does not equal +1, so the same y value came from two different x values, so it's not one-to-one. And the function on the left, f, is one-to-one. So let me give you a little proof that the function on the left is 1 to 1. So what we're going to do is start with 2 arbitrary elements in the domain. So let's let x1 and x2 be elements of the domain of that function, and the domain of that function is all real numbers. And then let's assume that f of x1 equals f of x2. So assume that you would get equal y values on that graph. And what we want to do is argue that those x values, x1 and x2, have to be equal. Okay, well, let's just do that. Well, we know f of x1 is 1/2 x1 minus 1, and we know f of x2 is 1/2 x2 minus 1. So that's just by the definition of the function, right? And then, you know, we can do like add 1 to both sides, and we get that equation, and then we can multiply both sides by 2, and we get x1 equals x2. And so now we know the proof is done. We started with f of x1 equals f of x2, and we arrived at the inputs x1 and x2 are equal. End of proof. Another property of functions that we want to look at is the onto property, or sometimes it's called surjective. The prefix of that word sur just means on. So here's what onto means. This is the sort of succinct definition of it. Function f from a to b is onto if the range of that function equals the whole codomain b. So the idea is that each element of b is the image of some element in a. So that's where we get the idea of onto, right? F is mapping a onto every element of b. So you just think about your codomain and think, is there always an element in the domain that yields that element in the codomain when you plug it into the function? So consider this function here. G is, we're defining it to be the map from R to R. So your B set here is all of the reals, and your domain A is all of the reals also. And you've got this formula. Well, we've seen a picture of this graph several times. It's just that upward pointing parabola that's shifted downward by 4. Let's see a picture of that again. Basically, what you can ask yourself if you're thinking about is this function onto is that is every element of the codomain a y value on the graph of that function? Well, when I look at the graph of G, I see that the y values on the graph start at -4 and work their way upwards, right? So I can see that the range of G is -4 to infinity. And that's not all of the real numbers. That misses all those negative numbers less than 4, right? So this is not equal to the reals. It's a proper subset. And so that tells us that G is not onto the reals. On the other hand, that other function we looked at just a minute ago, the linear function, it looked like this, remember? So when you examine the set of y values on this graph, you can see that the y values extend all the way from -infinity to +infinity. In other words, the range of f is equal to the real numbers here. And so that tells me that f is onto R here. So, you know, the key thing is you look at how the codomain was originally stated. In f, the codomain was R, and that actually is the range of the function. So that tells you that as that function is defined, it's onto. In the previous example, when we were defining G, the stated codomain was all of the reals. But when we examined the range of the function, it was -4 to infinity, not all of the reals. So that tells us that G is not onto all of the reals, but we could say, in the previous example, we could say G is onto the interval from -4 to infinity, which is its range. Every function is onto its range. So if we define G as a function from R to the interval -4 to infinity, then G would be onto. So the onto property has a lot to do with just how the codomain is picked in the first place. So if you're careful, you can always make a function onto just by insisting that the codomain B is exactly what the range of the function is. And that's great, but sometimes that doesn't make sense to do that because of what you're using the function for. Or sometimes it's very difficult to determine what the range of a function is, or to state what the range of the function is succinctly. So oftentimes the codomain is just sort of a common set, like all of the reals or all of the integers or something like that, that serves as sort of a vessel for what the possible output values could be, but maybe it's not exactly equal to what all the output values would be. Sometimes you're using functions to compare two sets also. So you have set A and you have a set B, and then you define a function between those two sets, and you're using that function as a way to compare those two sets. And so you don't want to change the codomain B. You want to leave it as is, and the function that you have just either is onto or not. But in principle, every function's onto its range, okay? That's the point of this. So next I want to give you a simplified version of what onto is. The definition we gave originally, that the range of f should equal b, means f is onto, is very concise. It's a good definition. But notice that if we already know that f is a function from a to b, and we use that notation there, that tells us already three things. And one of those three things is that the range of f is a subset of b. We also know that the domain of f is a, and that f is a function, are the three things that that notation entails. But see, we already know this, that range of f is a subset of b, and onto means that the range of f would be equal to b. So since we already know that the range of f is a subset of b, if we want to prove onto, we just need to prove the reverse containment. In other words, we need to show that b is a subset of the range of f. And if you think about what b being a subset of the range of f means, that means that just for every element in B, there exists an A in the set big A, such that if we did it in ordered pair notation, it'd be A comma B is in F. But since we're talking about a function here, we usually use the function notation. And so instead of writing A comma B is in F, we would say f of A equals B for what it means to be in the range. This is pretty nice. This is a different way to characterize the definition of onto that oftentimes is easier to work with. A function from A to B is onto if and only if for every little b and big B there exists an element little a and big A such that f of A equals B. And so that captures the idea that every element in B is the image of some element in A. So let's use that new form of the definition that I have in the box there to prove that the function below is onto. So the function we have here is 2x cubed minus 5, and it's being defined from the reals to the reals. And so we're wanting to show that this function is onto R. That's the codomain there, right? So this is the set that we want to show is the same as the range of the function. Now we already know that the range of the function is contained in that set, so we want to show that this set R is contained in the range. And so that's what the stuff in the yellow box captures. So here's our proof. So what we're going to do is start with an arbitrary element of big B. Now our big B set here is the reals. So let's call it Y this time. Let's let Y be an element of the reals. That's the codomain, right? So that's why I'm choosing that set. And so what we want to do, let me do a little scratch work over here. So given Y in the reals, we want to find some X in the domain of the function, and the domain of this function is the reals also, such that whenever we put X into the function, we want to get back Y. But that's the same as we need 2x cubed minus 5 equal to Y. So how can we find an X that satisfies that? Well, we can just solve that equation for X in terms of Y. So add 5 to both sides here, divide both sides by 2, and then take the cube root of both sides. And the nice thing about cube roots is you can take the cube root of a positive number, a negative number, 0, it doesn't matter. So the cube root of y plus 5 over 2 is in fact a real number because y was a real number, so y plus 5 over 2 is a real number. You're not dividing by 0 or taking square roots of negative numbers or anything like that to get y plus 5 over 2. So y plus 5 over 2 is a real number, and then when you take the cube root of that, you also get a real number. So x is definitely a real number. And so in this scratch work, I've identified what my x is that's in the domain that I need to plug into the function because all those steps were reversible. And when I plug that x value into the function, I'm going to get back y. So check it out. Now I'm going to go back to my proof, having done the scratch work. So then I'll say, consider x equals the cube root of y plus 5 over 2. And then we'll note that since y is a real number, then y plus 5 over 2 is a real number, and then so is the cube root of y plus 5 over 2. So x is a real number, because x is that cube root of y plus 5 over 2. So now I've identified an element in the domain. I'm going to emphasize that R is the domain of f here. Now, if you have an element that's in your domain, you can plug it into the function, right? That's what domain elements are. Domain elements are those elements that you're allowed to plug into the function. So now I can look at f of x and go, okay, well that's 2x cubed minus 5 according to the definition. And then that's 2 times the cube root of y plus 5 over 2 minus 5. And then if I cube the cube root, the cube root and the cube cancel each other, so I'm just left with 2 times y plus 5 over 2. Those 2's cancel and you get y plus 5 minus 5. And then those 5's cancel and you're left with y. So what I've just shown here, f of my x value equals y. Therefore, y is an element of the range of f, because I've shown that y is paired up with some element x in the domain as the second component of an ordered pair in this function. See, because I have f of x equals y, that's the same as x comma y is an element of f, right? So y is the second component of an ordered pair in that function, so that means it's in the range, according to the definition of range. And then that completes my proof, because I just showed that when starting at an arbitrary element y in R, that same y was in the range. So I just showed that R is a subset of the range, which is all we really need to argue to get onto. So this proof serves as a pretty good template for how you do basically any onto proof. You start with an element, arbitrary element of the codomain, so that's the B set, and then you show that element is in the range of the function. That's how all these proofs go. Okay, let's do a little skills check here on one-to-one and onto functions. So I have 3 problems for you here. The first one is we have a couple of toy functions from the set a equals 1, 2, 3, 4, 5 to the set b equals alpha, beta, gamma, delta, epsilon. And I just want you to examine which of these are one-to-one and which are onto. In the second problem, I've got a function defined from the natural numbers to the natural numbers. Now it's important to pay attention here that the domain is the natural numbers and the codomain is the natural numbers. And it has a pretty simple formula. F of n is equal to 3n. So I want you to show that this function f is one-to-one, but it's not onto. And then lastly, we have another function g that is from the natural numbers to the natural numbers. And the formula for the function is defined in a piecewise manner, but it's pretty straightforward. The way it works is the output is 1 if the input is an odd number, and the output is n divided by 2 if the input is an even number. So I want you to show that this function is onto, but it's not one-to-one. So take a few minutes to wrestle with those problems, and then when you come back, we'll work them together. All right, welcome back. So let's take a look at f and g here and see which of these are one-to-one and which are onto. Let's first think about both of them in terms of one-to-one. One-to-one means that you don't see the same second component paired with 2 different first components. So in other words, you don't see repeated second component. So for f, let's look and see if we see any repeated second components. Well, I think we do see a repeated beta in the first ordered pair and the last ordered pair. Beta is the second component, and then notice that the first components are different. So this is basically saying f of 1 equals beta and f of 5 equals beta. So that tells you that f is not one-to-one. And then onto, is the range has to equal b. So let's examine that for f. What is its range? Well, I've got alpha in the range, I've got beta in the range, I've got delta in the range, I've got epsilon in the range. Am I missing anything from capital B? Alpha, beta, I don't see gamma. There's no gamma in the range of f. So f is not on 2 either. I want to document my reasons for both of these. So f is not 1-to-1 because we saw that f of 1 was equal to beta, which was equal to f of 5, but those input values are not equal. 1 does not equal 5. So that violates the definition of 1-to-1. And it's not on 2 because the range of f was alpha, beta, no gamma, delta, and epsilon, which is not equal to the set B. Okay, now let's do the same thing for G. Is G 1-to-1? Okay, so let's see if we have any repeated second components. I got alpha, beta, gamma, delta, epsilon. No, I do not have any repeated second components. So that tells me G is 1-to-1. And let's look at the on 2 bit. So I want to know what is the range of G. So in the range I see alpha, beta, gamma, delta, and epsilon. That's all of B. So G is on 2. Also, range of G was equal to B. Okay. Okay, next let's look at number 2. I want to show f is 1-to-1 but not on 2. F is 1-to-1. We're going to prove that. So to prove a function is 1-to-1, you take 2 arbitrary elements in its domain. So we're going to take, let's say, n1 and n2 in the domain of f, which by definition is the natural numbers. And you suppose that you're getting equal output values. So suppose f of n1 equals f of n2. Then that tells me that 3 times n1 equals 3 times n2. And so we can certainly see that if we divide both sides of that equation by 3, we get n1 equals n2. And that's it. That's all you have to do, because we supposed that the function values were equal and we argued that the input values were equal. And we want to show f is not on 2. Okay. To be on 2, we have to have the range would be equal to all of n. But what I'm seeing is that the range is really just the multiples of 3. So anything that's not a multiple of 3 is not going to be in the range of f. So all I have to do is point out that, you know, there's some element of the natural numbers that's not in the range. So we're trying to show that the n does not equal the range of f. And you can show 2 sets are not equal just by demonstrating that there's an element of one set that's not in the other set. So consider, let's say, n equals 2 in the natural numbers. There does not exist, let's say, m in the domain, which is the natural numbers, such that f of m would be equal to n, for that would imply that 3 times m is equal to n, which in turn implies m is equal to n divided by 3, which is 2 divided by 3, because remember we said n is equal to 2. But 2/3 is not a natural number, and so you'd have a contradiction. So such an m can't exist, because if it did exist, it wouldn't be a natural number, which would be contrary to what our stated domain is. So there's an example where you're showing something is not on 2. And then on this third problem, we have another function, g, from the natural numbers to the natural numbers, and this one we're going to show it's on 2 but not 1-to-1. So g is on 2. So what we want to do is, remember we had a shortened, instead of having to show that the range equals n, we already know the range is contained in the natural numbers. We want to show that the natural numbers are contained in the range. So we want to show that for every n in the natural numbers, n is also an element of the range of g. So you'd want to start your proof by, say, like letting n just be some arbitrary element of the natural numbers, and then you want to figure out why it's in the range, and that means you need to come up with something in the domain that when you put it into the function, you get back that arbitrary n. Well, if you think about it, this function just takes half of every even number, but every number is half of something. It's half of twice that much. So consider m equal to 2 times n, which is a natural number. M is certainly even because it's 2 times an integer. So if I do g of m, because m is even, I use the second part of the piecewise definition here, and I take half of it to get what the output value is. And m over 2 would be 2n divided by 2, which is just n. So this shows n is an element of the range of G, because we just showed that m comma n is an element of G. So the range is just the set of all second components of ordered pairs in the relation, right? So there you go. That shows G is on 2. And now we want to show f is not 1-to-1. Well, to show the function is not 1-to-1, 1-to-1 means for every 2 elements of the domain, if the function values are equal, then the input values must have been equal to start with. So if you want to show not 1-to-1, you got to show there exists 2 elements of the domain where the function values are equal, but the input values were not equal. So can we come up with 2 different inputs that result in the same output is basically the question. Sure. Any 2 odd numbers give you the same answer, right? Because of the definition of this function, every odd number produces output of 1. If you let n1 equal 1 and n2 equal 3, and note that those are not equal, n1 does not equal n2, but g of n1 equals g of 1 equals 1, and g of n2 equals g of 3 equals 1. So we have g of n1 equals g of n2, but n1 does not equal n2. So that violates the property of 1-to-1. Okay, so next let's talk about bijections. So bijection really isn't anything new, it's just a combination of 2 things we already know. So a bijection is a function f from a to b that is both 1-to-1 and on 2. Sometimes instead of calling it a bijection, we call it a 1-to-1 correspondence. I actually prefer the terminology bijection though, because 1-to-1 correspondence makes me just think of 1-to-1. But sometimes you'll see people use that language, a 1-to-1 correspondence, for bijection. The idea of a bijection though is that you've got these 2 sets, A and B, and the function basically draws a unique arrow between an element in A and an element in B, so that every element in A is paired up with something in B and vice versa. So it's a sort of a way of pairing off the elements in a unique way between the 2 sets A and B. So that's where the correspondence stuff is coming from. Everything in A has a unique buddy, and everything in B has a unique buddy in the other set. All right, so let's prove that this function from r to r defined by f of x equals 2x cubed minus 3 is a bijection. We got 2 things to prove here. F is 1-to-1, and then separately we'll prove f is on 2. So to prove f is 1-to-1, we're going to take 2 arbitrary elements of the domain of f, and we're going to suppose that we get equal output values when we put x1 and x2 into the function. And suppose f of x1 equals f of x2, then we have 2x cubed minus 3 equals, that should be a x1, 2x1 cubed minus 3 equals 2x2 cubed minus 3. And you can add 3 to both sides of that, and you get 2x1 cubed equals 2x2 cubed. You can divide by 2 and you get x1 cubed equals x2 cubed. And then you can take the cube root of both sides of that and you get x1 equals x2. Whenever you take cube roots, you don't have to worry about absolute values and pluses and minuses and things like that. So that's it. We started with f of x1 equals f of x2 in the domain, and then x1 equals x2. So now let's prove separately that G is on 2. So we need to show that the codomain, which is R here, is contained in the range of G. We already know the range of G is contained in the real numbers just by definition of the function, so we just need to show the reverse containment. So let's let y be an arbitrary real number. And what we want to do is come up with an x value such that when we plug it into the function, we get back y. Usually you need to reverse engineer this by saying, like, well, y we want it to be equal to the, that's the function value. We want it to be equal to a 2x cubed minus 3. So solve for x. X cubed would be y plus 3. And then x would have to be the cube root of y plus 3 over 2. Forgot that 2 there for a second. So you would magically in your proof over here consider x equal the cube root of y plus 3 divided by 2. And you need to point out that this x value is actually in the domain. Okay, I'm going to hide my scratch work now. And note, this is a part that students often forget. Note that since y is a real number, it follows that x is a real number. Because, you're just taking the real number y, adding 3, that's still a real number, divide by 2, it's still a real number, and you can take the cube root of any real number and you get back a real number. And now you just want to point out that y is in the range because when you plug this x value into the function, you get back y. So we have f of x equals 2x cubed minus 3. That's equal to 2 times this cube root of y plus 3 over 2 cubed minus 3. The cube root cancels with the cubing function, so you get 2 times y plus 3 over 2 minus 3. And you can see that the 2's cancel and then the 3's cancel, and you're going to get back y. So this shows that y is an element of the range of G because y is paired up with something in the domain as an ordered pair in the relation G. And so now we've done what we needed to do because we started with an arbitrary element in the reals and we showed that that very same element's in the range. So that is what you need to argue that the reals are contained in the range. And then that proves you got a bijection because the function's both one-to-one and on-to. Okay, so next I want to talk to you about inverse functions. Now you may remember our previous discussion about inverse relations. Now we know that every relation has an inverse, and it's really simple to form the inverse of a relation. If you have a relation from A to B, to form the inverse, you get a relation that goes from B to A, and you form it just by taking all of the ordered pairs in the original relation and reversing the components. So since a function is a relation, every function has an inverse relation. The problem is that the inverse relation of a function may not itself be a function. So when you turn things around, you may not get a function. So this is something we need to investigate. What are the conditions that guarantee that when you take the inverse of a function, you get back a function? Because we know from experience in previous courses, in looking at things like inverse trigonometric functions and things like the inverse of a logarithm is an exponential, inverse functions play an important role in mathematics. So what we want to understand is, on a little bit deeper level, how do we know when we have a function that it's invertible in the sense that the inverse itself is a function? So let's take a look at this picture that we have here. I've got two functions, and they're both functions from A to B. You can tell that they're functions from A to B because every element in the set A has an arrow coming out of it, and every arrow terminates in B. So that tells me the domain and range are right. And also, I never have two arrows coming out of an element of A in either of these relations. So both of these functions, f and g depicted here, well, they are functions from A to B. But you'll notice that f and g are a little different in the sense that if we tried to reverse them, f would be really straightforward to reverse. But g, on the other hand, if you tried to reverse g, you've got a problem right here. When you try to reverse those arrows to form the inverse, well, you see that the inverse is not a function because you've got two arrows coming out of an element in B in the inverse. So what property does G not have that F does have that allows F to be invertible? Like F it's easy to see. All these arrows, you just simply turn them around, right? And you got a nice function from, at least you got a function from not all of B to A, but you got at least got a function from a subset of b back to a. So f inverse is a function. In fact, f inverse is a function from the set a, b, c, not including d, back to a. G inverse is not a function because 3 comma z and 3 comma w are elements of G inverse, but z does not equal w, so that's why G inverse is not a function. So observe f is 1 to 1. That's the key property here, and G is not. G not being 1 to 1 is what really causes it to not be invertible. See, the 1 to 1 property forbids this sort of behavior here where you have 2 different inputs resulting in the same output. If that ever happens, you can't turn it around into a function, right? Now, f isn't perfect. I couldn't make f inverse a function from all of b back to a. I could only say f inverse was a function from a subset of b back to a. If we wanted f inverse to be a function from all of b back to a, we would need the range of f to be all of b, right? We couldn't have any leftover elements like that. And when you have leftover elements like d there in the function f, that means that f was not onto as a function from a to b, right? It missed some things. It wasn't onto all of b. So if we want to have sort of a perfect inverse, we would need f to not only be 1 to 1, we would need it to be onto. Let me write some of that down. So if we wanted f inverse to go from all of b to a, it's pretty clear from that diagram we would need f to be onto as well. So you need 1 to 1 just to get an inverse, but then if you want it to be an inverse from the whole codomain back to a, you need onto as well. So what we're seeing here is that in order to get a really good inverse, you need to start with a bijection, 1 to 1 and onto. So consider these. Here's a couple of functions here. 2x plus 6, that's a linear function. And you may remember back in high school that you probably were taught a process for finding an inverse of a function when it exists. Now, this function, f of x equals 2x plus 6, is a linear function. You know, it just kind of cuts through. It's, you know, just a line with slope 2, y-intercept of 6. I'm not going to bother graphing it. I think you can imagine that or graph it for yourself. But it's 1 to 1 and onto. In other words, it's a bijection. And the process for finding the inverse goes something like this. You'd have, like, say, f of x equals 2x plus 6. I remember clearly learning this in high school. You replace f of x with the symbol y, just for convenience. Makes it a little simpler. And then remember, when you form the inverse, you interchange the first components and the second components of all the ordered pairs in the relation. So in terms of this equation, I would just interchange x and y. So I'm going to make x equal 2y plus 6. And then I'm going to solve for y. And so if you solve for y there, you get y equals, let's see, x minus 6 over 2. And that's f inverse of x. So f inverse of x is x minus 6 over 2. And the fact that we didn't run into any weirdness in solving for y in this process tells me that I actually do get an inverse. And so it turns out that f inverse here is a function from the reals to the reals. And it's defined by this equation, f inverse of x is equal to x minus 6 over 2. Now, on the other hand, let's look at this function g here. Now g, 2x squared minus 3, that you probably will recognize as a parabola, and it opens upward, it's shifted down by 3. But I know parabolas always fail the horizontal line test. Horizontal lines always cross parabolas more than once. So I know this function is not 1 to 1, and that turns out that it's going to be, tell you that it doesn't have a good inverse. So here g is not 1 to 1. It's also not onto, because the range of this function is the interval from -3 to infinity, which is not all of the real numbers. Now, if you would try to do that process for finding the inverse, like I showed you above with f, you're going to run into trouble. So you do the same thing, replace g of x with y, interchange x and y, try to solve for y now. So you get 2y squared equals x plus 3, divide by 2, you get y squared equals x plus 3 over 2, and then now if you take the square root of both sides, you're going to get absolute value of y on the left-hand side. There's also, so anyway, you end up with, y equals plus or minus, depending on what value of x you originally started with. And also, you may notice that you don't want to get negatives inside the radical, so you have to restrict x to be greater than or equal to 3. If x is not greater than or equal to 3, this doesn't make sense. So that's telling you that unless you restricted your original domain to be x is greater than or equal to 3, you would get all kinds of ill-defined things where you get negatives in the radical. So we start to see the algebra gets a little screwy here in this region of the process. And the reason you're getting that screwiness is because of the lack of one-to-one and on-to properties. The lack of one-to-one is causing this plus and minus here, because that plus and minus reflects the fact that there are 2 x values for every y value in the original function. So whenever you do the inverse, it gives you 2 y values for every x value, because you switch x and y. And the fact that we had to make this restriction here is telling you something about the original function not being onto, because the range of the original function was -3 to infinity. I should say x is bigger than or equal to -3 here. So we don't get onto-ness, and it screws things up a little bit too. With those examples in mind, let's take a look at a couple of theorems here. Theorem 4.17 tells you, well, that minimum thing that you need in order to get an inverse for a function is that it needs to be 1-to-1. So the theorem says if f is a function from a to b, okay, we're assuming that. So f is a function, its domain is all of a, and its range is contained in b. Then the condition that f inverse is a function, that's what this notation indicates, with the domain of the range of f and a codomain of a, like that only happens when f is 1-to-1 and vice versa. If f is 1-to-1, then this happens, but it's an if and only if. So if the inverse is a function like that, then it tells you the original function was 1-to-1. So it goes both ways. That's sort of the minimum you need in order to be able to talk about an inverse as a function. Now, you don't get necessarily the domain that you want for the inverse. You'd like it to be b, right, if you're just thinking about reversing f. But you can't quite reverse everything because the range of f might not be all of b. So you can only reverse those things that are in the range of f. Of course, we could fix that if we knew the function was onto, but we'll deal with that in the next theorem. So let's prove this theorem. This will be good exercise for dealing with inverses and 1-to-1 and, well, lots of things. Nice proof technique proving a biconditional. This is a really good theorem to prove. It really flexes our muscles in a lot of different ways. So let's do this proof. And like I said, it's a biconditional. So we have 2 directions to prove, the forward implication and the reverse. We have a global hypothesis here. So let's assume that at the very beginning. So suppose f is a function from a to b. So we know that the domain of f is equal to a. The range of f is contained in b. And we have the function property. I'll say now let's prove the forward implication. So we'd start this by supposing that f inverse is a function from the range of f to a. So this means something. This means what we're supposing is that 1, that the domain of f inverse is equal to range of f. 2, it means that the range of this f inverse is contained in a, the codomain of that. And 3, f inverse has the function property. That just means that equal inputs will yield equal outputs when you plug them into f inverse. So now what we want to do is prove that f is 1-to-1. To prove f is 1-to-1, let's let a1 and a2 be arbitrary elements of the domain of f, which we know is equal to a by the hypothesis at the very top of the proof. And we need to suppose that when we plug those 2 elements, a1 and a2, into the function f, we get equal outputs. So, and suppose f of a1 equals f of a2. So when you're dealing with inverses, it's often easier in your proof to convert things into the ordered pair notation, because we know that the inverse is just where you take the original relation and reverse the order in the ordered pairs. So if I would let, say, b1 equal f of a1, and if I would let b2 equal f of a2, then what that means is that a1 comma b1 as an ordered pair and a2 comma b2 as an ordered pair is in the relation f. And now if I want to talk about things being in the inverse, I just have to reverse those ordered pairs. So thus, b1 a1 and b2 a2 are elements of the inverse. Now check it out. What do we know about b1 and b2? Well, b1 is equal to f of a1 and b2 is equal to f of a2, but we know f of a1 and f of a2 are equal over here. So that tells us that these two elements right here, b1 and b2, are equal. And they're the first components of an ordered they're the first components of ordered pairs in the function f inverse, which we've assumed was a function. Because b1 equals b2 and f inverse is a function, then equal inputs have to yield equal outputs. In other words, if you have equal first components, then the corresponding second components have to be equal. So we have a1 has to equal a2. Now check it out. We've completed the proof of one-to-one because we started with f of a1 equals f of a2, and we just arrived at a1 equals a2. And that's how you know when you're done doing a proof of one-to-one. So we've established the forward implication. Now we're ready to do the converse. So to do the converse, we're going to assume that our function is one-to-one. And then to prove f inverse is a function from the range of f back to a, we have to establish those three things. So we must prove, one, that the domain of f inverse equals the range of f. Two, we got to show that the range of f inverse is a subset of a. And three, we got to show that f inverse has the function property. Okay, so we'll do these things in turn. So one, that domain of f inverse equals the range of f. Well, this is a general property of relations that we proved back in the chapter on relations. Back in the chapter on relations, we had a theorem. I don't remember the reference on it right off the top of my head, but it said that the domain of a relation R is equal to the range of that relation's inverse. And then it also said that the range of R is equal to the domain of its inverse. So we had this theorem that gave us that for free. So we don't need to reprove it, it's just a general fact. Two, we need to show that the range of f inverse is contained in A. In fact, we can do better than that. The general property that I just mentioned a minute ago, right here, I've got it written in the reverse order, but the range of R inverse is equal to the domain of R, so we know that range of f inverse equals the domain of f, which by hypothesis, right here, we know that the domain of f is equal to A. So not only is the range of f inverse contained in A, it's equal to A. Whenever two sets are equal, you get double containment, right? So in particular, I know if range of f inverse is equal to A, well, it's certainly contained in A. Also, A is contained in it, but we don't need that. Okay, the third thing is we got to show that f inverse has the function property. So to show something has the function property, you take two elements in its domain. So let b1 and b2 be elements of the domain of the inverse, which we already showed was equal to the range of f. And we need to suppose that those two elements are equal. So with b1 equal to b2. Then we want to show f inverse of b1 equals f inverse of b2, essentially. We want to show that when we put those two numbers into the inverse, we get that they correspond to the same thing. Because we know b1 and b2 is in the domain of f inverse, because of this, then we can use the definition of domain to call into existence elements that pair with the b1 and the b2. So since b1 and b2 are in the domain of f inverse, there exist a1 and a2 in the range of f inverse that pair up with that b1 and b2. So such that, okay, they're in the range, so the a1 and the a2 are in the range, so they're the second components, and the b1 and b2 are in the domain, so they're the first components. So you get b1 comma a1 and B2 comma A2 are in F inverse. But see, I want to use what I know about the original function f being 1 to 1. So what I want to do is use the fact that these ordered pairs are in the inverse relation. I can reverse the order of the components and get something in the original function. So A1 comma B1 and A2 comma B2, reversing the order, those ordered pairs are in the original function, and we have B1 equals B2. So notice now we're talking about things in the original function, and those second components are equal. B1 equals B2. Well, remember, our function f is 1 to 1. And when a function is 1 to 1, the property is that when the second components are equal, then the first components have to be equal. So since we could put this in the function notation to make it a little clearer, we could say that f of A1 equals B1 equals B2 equals f of A2. And then since f is 1 to 1, and you have those equal outputs, and f of A1 equals f of A2, we have A1 equals A2. And that's exactly what we wanted, because what's another name for A1 and A2? A1 and A2 were the second components of those ordered pairs, where B1 and B2 were the first components. So putting that into the functional notation for F inverse, we could rewrite that as that is F inverse of B1, that's A1, right, because of this ordered pair right here. That ordered pair being in F inverse tells you f of B1 equals A1. And then the second one here says f of B2 equals A2. And we know A1 equals A2, so we have F inverse of B1 equals F inverse of B2. And that's it. That's what we needed to show, because we're trying to prove that F inverse has the function property. So the way that works is you start with equal inputs, and then you argue that you have equal outputs. That's the function property. And so there we have it. This proof really has a lot going on in it. So this proof, you really, I would expect that you want to spend a little time getting intimate with this theorem and really trying to absorb it. There's a lot going on there. Okay, we have another theorem before we wrap up we need to talk about. Okay, so this theorem you can kind of view as the completion of the previous theorem. It's like, okay, now we're going to add a little bit of extra property onto f. So now if we assume that f is 1 to 1 and onto, then under those conditions we know that the inverse is 1 to 1 and onto as well. And notice that it's a complete reversal. F is going from a to b, and then the inverse function is going from b to a. And if one is 1 to 1 and onto, then the other one is onto 2. This could be stated as an if and only if theorem, because it's certainly true that if the inverse function from b to a is 1 to 1 and onto, then its inverse, so f inverse is just f, so it goes the other way too. But you don't need to state it as an if and only if. It's enough to just state it in this form, because you sort of for free get the converse just because of that f inverse equals f property. Anyway, let's prove this theorem. Now we can make use of our previous theorem 4.17 here. That's going to be a big aid to us to make this next proof a bit shorter. So let's suppose if going from a to b is 1 to 1 and onto, I could just say is a bijection if I wanted to, because bijection just means 1 to 1 and onto. First, let's observe that f inverse is indeed a function from b to a, i.e. domain of f inverse equals b, range of f inverse is contained in a, and f inverse has the function property. We know as a general property that the domain of f inverse is equal to the range of f, and we know that the range of f, on account of f is a function from a to b and it's onto, then we know the range of f is b. So this bit right here checks out, and then we know that the range of f, just as a general property of relations, is equal to the domain of f. Range of f inverse is the domain of f, and we know the domain of f is a, and so that tells me that the range of f inverse is a subset of a. So this thing checks out that the range of f inverse is a subset of a. And the previous theorem, theorem 4.17, provides that f inverse has the function property, because we have f is 1 to 1 here, and that's what the previous theorem said. The previous theorem said that if f is 1 to 1, then your inverse function is going to have the function property. Okay, so we know that f inverse is a function from b to a, and now we want to establish a little bit more that that inverse also is 1 to 1 and on 2. So let's point out why f is 1 to 1. To see why f is 1 to 1, we're going to we want to show f inverse is 1 to 1. We want to let b1 and b2 be elements of the domain of f inverse, which we know is b. And we're going to suppose that when we plug those numbers or those elements into the inverse function, we get equal outputs. So we're supposing f inverse of b1 equals f inverse of b2. If we let a1 equal f of b1 and a2 equal, f inverse, keep forgetting my inverse, f inverse of b2, then we have a1 equals a2. And we know b1 comma a1 and b2 comma a2 is an element of f inverse. Now, using the definition of inverse, we know that a1 b1 and a2 b2 are elements of f. And because f has the function property, see, we've got two ordered pairs in f, and those two ordered pairs have the same first component, because remember a1 and a2 are equal. So if those first components are equal, the function property tells us that the second components have to be equal. So we can say, since f is a function, b1 has to equal b2. Well, if you take a look at what we just did, we started by supposing f inverse of b1 equals f inverse of b2, and then we argued b1 equals b2. That establishes that f inverse is 1 to 1, and then we need to show f inverse is on 2. Actually, I think this won't be hard to establish, because remember, the original definition of on 2 was that the range needs to equal the codomain. We know that the range of f inverse is equal to the domain of f. That's just a general property of relations, but we know by hypothesis that the domain of f is equal to a. So range of f equals a. So f inverse as a function from b to a is on 2, because the range of f inverse is equal to the codomain, which is that set A. So we have range of f inverse equals a, and that's the codomain over there. So that's it. That was kind of for free. So this is a really nice property. Every time that you have a every bijection has an inverse, which is also a bijection, which is good. So if you think of bijections as just sort of pairing the elements in one set with the elements in the other set, you know, it's nice to know that the pairing goes both ways, right? Okay, let's finish this lecture with a skills check. This one's pretty short, just one problem. I've got a function for you, and it's defined from the positive real numbers to the real numbers, and it's our old friend, the natural log. Dun dun dun. People get tighten up a little bit sometimes when you start talking about natural logs. So I want to prove that this function g, the natural log function, is a bijection. And then I want you to think about, what does that previous theorem that we talked about tell you about the inverse of this function g, which is the natural log? And lastly, I want you to think about, what is the inverse of the natural log function? This may be something, if you rack your brain and think about things you did in previous courses, this function g inverse has a more common name than just g inverse. It's a common function that we use a lot. So think about that and press pause, and when you come back, we'll work through this one together. All right, welcome back. Okay, let's prove g is a bijection here. Now this is going to have to rely on some previous knowledge of functions, but that's okay. We can rely on stuff that like we did in calculus and whatnot. So A. So first let's start by proving g is 1 to 1. So take x1, x2 in the positive reals, so the interval 0 to infinity, and suppose g of x1 equals g of x2. then that means that natural log of x1 equals natural log of x2. Now you may remember some properties about how the natural log interacts with exponential functions. So we could do something like e to the natural log of x1 equals e to the natural log of x2, because we're using another function we know about, the exponential function, and using the fact that it's a function, and if I put equal inputs into it, I get equal outputs. But then we know that e to the natural log of something is just that something, so you get x1 equals x2 here. And then there you go, you have started from the premise that g of x1 equals g of x2, and you've arrived at x1 equals x2. That's 1 to 1. And then to do g is on 2. Now here we got to show that the range of g, we need to show that R, the codomain up here, is contained in the range of g. So start by taking an arbitrary number y, let's call it, in the reals, and I want to show that I can produce y as an output of some input. So I have to find an input that I can plug into the natural log and I get back y. So a little scratch work over here. If you want y equal to natural log of x, what would x have to be? Well, if you exponentiate both sides, you'd get e to the y has to be x. So that's the x that I need right there. So I'll say, consider, let me erase my scratch work now. Consider x equals e to the y, and note that e to the y is a real number for any y in the reals. So x is a real number. Not only that, also e to the y, you may remember, is greater than 0 for all y. So our x, which is equal to e to the y, is greater than 0. So x is a positive real number, thus x is in the domain of g here, which was the interval 0 to infinity. You always have to make sure that this x that you come up with in these proofs of onto-ness has to be something in the domain. It's a common mistake if you don't check that your element is in the domain. All right, so now we've got an element in the domain, and we reversed engineered it so that when we plug it into the original function, we're going to get back y, but let's verify that. So now we're going to take g of x, well, that's g of e to the y. So that's natural log of e to the y. And natural log of e to the y, you may remember from properties of logarithms, that's just y. So we just pointed out that g of x equals y. So that tells you that y is in the range. So this shows y is in the range of g. So we started with an element here, y, in the real numbers, and we argued that that very same y is in the range, and that shows you that the real numbers are contained in the range. And the range was contained in the real numbers by definition of the function, so this really shows you that the real numbers equals the range of g. So that's what it means to be onto there. All right, so what we just found out is that the natural log function, when you define it as a function on the positive real numbers to the real numbers, it's a bijection. And if you think about the graph of the natural log function, that's not a big surprise. The graph of it looks like this. And you can see that the range of that is all real numbers. Now, as you move out far to the right on the graph, it rises very slowly, but it keeps going up forever. It doesn't have any upper bound. So it stretches from negative infinity to positive infinity on the y-axis. And you can put any positive real number that you want to in there, but it never crosses the y-axis. So it stays, the graph stays to the right side of the y-axis. All right, so that function there, though, is a bijection. And so what does theorem 4.18 tell us about G inverse? Well, let's go back and look at theorem 4.18. Well, here we had a G function from 0 infinity to the reals, which was a bijection. So that tells us that G's inverse, whatever it is, goes from R to 0 infinity is a bijection. So applying 4.18 here, it tells us that G inverse which will map from the real numbers to the positive reals, is a bijection. So the inverse of a bijection is a bijection, and the domain and the range are just switched, interchanged from the original one. And C, I ask you, what's the common name and notation for this function G inverse? Well, G inverse is just our old friend, the exponential function, the natural exponential function, e to the x. So e to the x and natural log of x are inverse functions. All right, we'll stop there. Maybe I'll have a little recap of what we talked about here. So there was a lot. This is a pretty big lecture, really important stuff here. We defined what we mean by a function. And, you know, initially, when we first started talking about functions, way back here, we talked about functions in terms of ordered pairs. So the sort of function property was that whenever a comma b is in f and a comma c is in f, then b equals c. So if you have equal first components, then you have equal second components. We talked about what this notation means, the f colon a arrow b notation. We talked about what that means. It means these three things down here. And that's really important because we use that a lot. We talked about functional notation. So f of a equals b means the same thing as a comma b is an element of f. That's important because sometimes in proofs it's more convenient to switch over to the ordered pair notation, especially when we're talking about inverse functions. The functional notation allowed us to recast the definition of function like what we have in the box here. And so we can think of that as equal inputs implies equal outputs when you're talking about the function property. We talked about a vertical line test for just visualizing if a function is, well, if a relation is a function. Well, that's something you probably talked about in some previous course, but now maybe it makes more sense. The vertical line test is just saying, you know, if it crosses that graph twice, you've got an x value that corresponds to two y values on the graph. So that's one input gives two outputs, and that's what you're trying to avoid on a function. And as important as talking about, you know, how to prove things are functions, we also need to sometimes watch out for how do we know when something is not a function. So we went through some proofs of things either are functions or not functions. So these proofs are important. And then we did the properties of functions. The big properties were one-to-one and onto. One-to-one just means that if two outputs are equal in a function, they must have come from the same input. So you can kind of think of it as each output value of the function is unique. You don't get the same output value two different ways. Onto just means that the range is equal to the whole codomain. So every element in the codomain has an arrow pointing toward it in the function, right? So, and when the function's both one-to-one and onto, we call it a bijection. And bijections are nice because it puts two sets in a correspondence. It allows you to sort of like buddy up the elements in the two sets. That's something that's really important as you move into higher level maths. Whenever we have two algebraic structures called groups and we want to say that they're really the same group but just look different, we need to, like, first and foremost, we have to establish a bijection between those sets to make sure that those two sets basically have the same number of elements, so the elements can be paired off in those two sets in a special way. And then we did talk about inverse functions as well, and we talked about how you can tell when the inverse of a function is actually a function itself. And the key property you need to get an inverse that's a function is one-to-one. But if you want it to be a really nice inverse function, you want to have the bijection property, because the bijection, if you have a bijection, its inverse is also a bijection, and the codomain equals the range, and so you can just switch. Like if f goes from A to B, then f inverse goes from B to A, and everything works out really nice. But probably the biggest thing that we've looked at besides these concepts are some of the techniques of proof. Like the proof techniques that we've been doing in here, really you need to sit down with them, because we're going to be using them a lot as we move forward to start talking about compositions of functions, and when we start talking about how images and pre-images interact with set operations like intersection and union. We're going to be doing a lot of proofy stuff in the next few sections, and we laid the groundwork for it here in section 4.2 and 4.1 to a degree. But yeah, you got to spend some time with these proofs and be able to replicate them. So like I said, I'll stop there and talk to you again soon. Bye.